Well, you should first wait to hear the talk. I will speak about not as advertised, but as random walk on half-planar maps, which seems very appropriate for this workshop. So this is so I will mainly speak about joint work with Gura Bray. But I will also mention some earlier works, and depending on time and on what sort of questions you ask and how things are pushed, so Asaf Nachmias and Tom Hatchcroft and some other interesting people might also come up. But I'll leave this to you. But before I start, I should first thank the organizers for the invitation to speak here and for this lovely place. I guess the only complaint perhaps is that the lecture room is a bit too far from the beach. So, or alternatively, the lunch breaks are too short. You can't have both, and you should maybe look to UBC where we arrange things with the new beach just below and not half an hour away. But so thank you to the organizers, at least the organizers who are present. The third organizer has a second career in the adult entertainment business. In the sense that it's mainly entertaining for adults, but this lecture is being taped and broadcast, so if you're watching from home, hello, Gregory, and thank you. Yes, so this is being taped, so I understand people in the front might also show up on the video, but okay, so let's start with half-planar maps, and at this point, I think everybody here knows what a planar map is. And I'll start with a question of Benjamin-Schramm. And this is around, more or less around 2000. Is the UIPT recurrent? So they asked this question at the time we didn't have the UIPT. If you're not familiar with the specific this map, I will say what it is. But at the time, it was not yet known to exist. That came later, but they wanted to know if it's recurrent. And actually, they had the first part of a proof that it's recurrent at that time. And they had the following theorem. So I'll define what I mean by this in a second. But if you have a graph G, which is a limit of graphs Gn, and Gn are finite, planar, and have bounded degrees, then G is almost surely recurrent for the random walk. So there's no dynamics on the graph. Now you all know what finite planar graphs with bounded degrees are. So the bounded degrees are for all of them together, not individually. A single finite graph has bounded degrees. And the limit is the weak local limit, which some people call the Benjamin-Schramm limit. There's some debate whether this is an appropriate name or not, but this is the local limit in the sense that you take a root uniformly for the graph. So given the graph Gn, you choose uniformly root rho n. And you take, so rho n is a uniform root. And you take the limit of this in the local topology in the sense that if you look at any finite neighborhood of the root, then you get, you see the same, asymptotically the same sequence of graphs, or at least in distribution. That's the weak part. Yeah, so this converges in distribution to G rho. What is the UIPT now? So the UIPT is exactly the limit if you take Gn to be a uniform triangulation, a uniform sphere triangulation with n vertices. So this is certainly planar by definition, but they don't have bounded degrees. The highest degree is logarithmic. So a few years later, with Oded, we proved that the UIPT indeed exists. There is a limit. And this has been extended since then. So Krikun wrote about quadrangulations. And now we know for many other classes of planar maps, if you take Mn to be some planar map which grow to infinity, uniform in some reasonable class, then Mn, so the limit of Mn exists in the weak local sense. So this is a fairly universal principle. And the limits that you get for triangulations, you get the UIPT. For quadrangulations, the UIPQ. And you have the uniform infinite planar maps in the various other classes. And OK, so we have this condition of having bounded degrees. And this appears in the Benjamin-Schramm proof, which I will review later on. It appears in some crucial places. But later on, eventually, Ori Gurel-Gurevich and Asaf Nachmias proved that the UIPT is recurrent. And in fact, they proved even more. They proved that if Gn are planar and they have, instead of bounded degrees, they have a uniform exponential tail on the degree, then the limit of Gn is recurrent. So they replaced the bounded degrees by a uniform exponential tail. This just means that the probability that the degree of the root is larger than k is less than e to constant k for some constant for the same constant for all n. And it was already known that the UIPT and that the random map on n vertices in any reasonable class has an exponential tail on the degree. So perhaps not any reasonable class. So we've heard about some classes where you don't have exponential tail, where you have a power tail. But certainly for these uniform maps, you have an exponential tail. So this finished this part of the proof. Well, there's another condition here, the planarity, which also you might ask, is this really necessary? And so it can be relaxed somewhat in the same way that bounded degrees. So if you completely remove it, there are examples of graphs which do not have exponential tails, slightly weaker control of the tails, and the limit can be transient. So if you completely forget about planarity, of course, it's possible to get transient graphs in the limit. That's easy to give examples. I'll leave this as an exercise, but I shall mention some work with Balázs Szegedy, which I will not talk about today. But so essentially, it's the same theorem as Benjamin-Schramm, but we replace planar by excluded minor. So if you have a family of graphs with some constant excluded minor, the limit also is almost surely recurrent, and this is still with bounded degrees. And if there's some enterprising student, they might try to combine these two to get the exponential tail in this case as well. So most of the pieces are in place, but it doesn't seem there's anyone willing to do this at the moment. There are a couple of difficulties. It's not all there. So this is the story of the UIPT. And now that we have the UIPT, I'm going to move to the half UIPT. You cannot move two boards at once. That's, is there a reason for this? You can move two boards at once. Good. So just not... we'll try in a few minutes. We'll see. So so what is the half UIPT? This has not come up in any of the talks, I think. So I will say a bit more about this. So suppose you take some triangulation of a disk. So we've seen a few of those. So you take a triangulation of the disk where the boundary has size m and the interior has n vertices. So you have m on the outside and on the inside. So and you take one of those uniformly. Now, for now, I'm going to assume that the boundary is simple. So there is an analogous version with non-simple boundary, and the difference is not interesting for us. So I will assume the boundary is simple. And we have a root which we assume to be on the boundary. So and now we take a local limit of those. So this is no longer the same local limit of graphs with a uniform root. Now the root is constrained to be on the boundary. And because the root is constrained to be on the boundary, then near the root, you see something which has, on one side of the root, you have a very large face. So what we do is we take a limit of, let's call this Tmn, which is the uniform triangulation with these parameters. I take a limit, and I take the limit as n goes to infinity, and I take the limit then as m goes to infinity. And this is the half UIPT. So it's the half-plane uniform infinite planar triangulation. And in fact, you can do a bit more with this. You can even say that if you take the limit of Tmn, where m and n both go to infinity together, as long as n is much greater than m, so n over m also goes to infinity, then you also get the half UIPT. If you take instead m proportional to n, then you get some hyperbolic half-planar maps, which I will also not get into unless people really push me this way. And if you let m be larger than n, then you get something very tree-like, which in the large scale looks like a random tree. So, and also, those are different stories. So, so we get this limit, and what does this limit look like? So we have the root edge, which is of course yellow. And we have the boundary. So on one side of the root edge, since we let m go to infinity, on one side we see an infinite face. If anything is not clear, do interrupt me. So here we have an infinite face, and on the other side we have a triangulation. So we have just triangles everywhere filling the plane. That's not a triangle, but yeah, sometimes it's difficult to draw triangles. You try, and however how hard you try, you get squares and pentagons. But so this goes on. So there's no specific embedding in the plane that I'm using at the moment. So this is just a map, so I only care about the combinatorics. So this is the half UIPT. And the natural question, so this half UIPT has been around for about as long as the UIPT. So it's implicit in the earliest papers. And there's a natural question, is this recurrent or not? Nicolas? Yeah, well, okay, so Nicolas knows. The answer is that it is recurrent, and this is the main theorem that I will talk about today. That the half UIPT is recurrent, indeed. Now, at this point, some of you may be wondering, so if you have something like a random walk in the plane, and we know that it's recurrent, and now if we have a random walk in the half plane, and we want to know that it's recurrent, then this is something that we give to any first-year student, and they tell us it's easy because it's a subgraph. And if you take a recurrent graph and take a subgraph, then it's also recurrent. Except that this is an open question. Is the half UIPT a subgraph of the full plane UIPT? Is it possible to take a coupling of the two so that one is a subgraph of the other? And the answer seems to be no. A different student that you ask the same question might say, if you have the half plane, if you have a random walk on the half plane, you can just think of it as folding the full plane. You have the full plane and you fold it, and the random walk projects to the random walk in the half plane. And it's recurrent in the plane, so it's recurrent. So this is known not to be the case. So there's an argument due to Nicolas. So if you take two half-plane UIPT, and you take a second one, and you glue them together, then this is not the UIPT. It's quite different. Did you write this at some point? I don't remember.
It will come soon. It's with Alessandra Carafin. It will come soon.
Okay, so this is so this certainly does not work, and okay, and there's the more general question here, which is left here, but so this doesn't work. So how do we prove that it's recurrent? And well, so to answer this, I'm going to review some of the ideas from the proofs of Benjamin-Schramm and from the proofs of Gurel, Garevich, and Nachmias. And in a sense, what we use both of those ideas, but we effectively what we have is a theorem. Which a more general theorem, which I'll perhaps try to state later. But right, so if there are any questions about where we are going, now would be a good time, because I'm going to start going into some details. Okay, so let me say a few words about circle packings, which are the first ingredient. So So you'll have to excuse my circles, which are not perfect circles. What's that?
It's not their fault. You said you have to excuse my circles.
Yes. Well, whose fault is it then? Yeah, it's a very long walk from the beach. So we have a collection of circles in the plane. We assume that they have disjoint interiors, and we associate a vertex to each circle, which we might place at the center of the circle. And we connect two circles if two vertices if the corresponding circles are tangent. Like so. And you observe that you get a planar graph in this way. In this case, it's even a triangulation. Yeah, you can move all three. So the circle packing theorem, in its first form due to Kebe, then generalized by Andreev and Thurston. So any finite planar graph G has a circle packing, in the sense there exists a configuration of circles that realizes the G as the tangency graph. And it's unique for triangulations. Well, it's unique up to some degrees of freedom, which are Möbius transformations. So Möbius transformations preserve circles and tangencies. And this is true for finite planar graphs, and this has been extended by a sequence of works, including Schramm and Hennenfent. This also holds for infinite graphs. And for infinite planar graphs, the uniqueness is slightly less general. For infinite planar graphs, we have two possibilities. And this is, I should mention here, this is due to Hennenfent. So we have a dichotomy. Either the circle packing is locally finite, in the sense that you have no accumulation points for the circles, or else it's supported in some domain D, which is contained and not equal to the entire plane. And in the second case, you have a lot of flexibility in choosing the domain. These are very similar and closely related to conformal maps, and in the sense that any two domains are conformally equivalent, you can more or less choose your domain here. In the locally finite case, you do have what's called rigidity or uniqueness, and in this case, it's unique. Up to, well, in this case, the degrees of freedom are Möbius transformations preserving infinity, so just linear transformations. So just similarity and rotations and translations. So it's unique in a slightly weaker sense. And they also proved, yes? Yes, the uniqueness is for triangulations. If you have a quadrangle, for example, you can see that there's no uniqueness because you can add an edge one way or the other. And this would force this circle packing or this configuration of circles. And you can also interpolate. You can also say, let's put a vertex here and connect it like this. This will force a circle packing with a common circle inside tangent to all four. And you can put anything you want inside the circle. So you really have quite a lot of things. You could, there are some extensions of this. There are some generalizations of this which give uniqueness for non-triangulations. So when you take a circle packing of the graph and it's dual together, there are several variations on this which do give a rigidity for more general maps. But I'm going to stick to triangulations for now. Actually no, I'm going to talk about, I'm going to use circle packings for other graphs, but I don't really need the rigidity for what I need. What I do need is that this dichotomy depends only on the graph. So any graph falls either in this category or in this category. And it's impossible that you have both types of circle packings. Yeah, there's a slight additional point on which I'm slightly cheating, that the graphs need to have the plane topology. So you can have, for example, a graph. You can take a graph where you have a face and you put inside it something like that, and inside it you put something like that, and you can keep doing this, and you can put something infinite inside here within. So this is certainly a planar graph. And you can find circle packings for this, but they would necessarily have an accumulation point here. So I assume that you don't have any accumulation points for the graph itself. So we assume the graph has, as a map, we assume it has a plane topology. But this is a... if you have bounded degree or finite faces, then yes. If you have, if all faces are finite, it's the same as being one-ended. So we have this existence, and again, due to Hennenfent, this is closely related to recurrence and transience of the graphs. So if G has bounded degrees, so it is circle packing parabolic. So this is called circle packing parabolic, and this is circle packing hyperbolic. So it is circle packing parabolic if and only if it is recurrent for a random walk. And again, if you think of the connection to conformal maps, and you should think of this as similar to a conformal type, so of a manifold. So if you have a manifold which is conformally equivalent to the plane, then it is recurrent for Brownian motion. If it's hyperbolic conformal to a subset, then the Brownian motion will hit the boundary, and it is transient. And well, they do need the bounded degrees in order to prove this. The reason that they prove this is that, well, recurrence is equivalent to saying that if you have any flow of a mass from a root to infinity, then the sum of the flow along the edges squared, this is just as a comment, this is equal to infinity for every flow. So the sum over the edges. And circle packing, so this, or let's make it, let's talk about recurrent graphs. So a graph is recurrent if, recurrent, yeah, this is recurrent. So it's recurrent if for every flow this is infinite. And it is circle packing parabolic if for every flow the sum of f of v squared is infinite, where the f of v is the total flow going through a vertex. And of course, if you have a final, if you have a uniform bounded degrees, if one of these is finite and the other is finite. And in one direction, you don't need the bounded degrees also. But in order to deduce recurrence of a graph, you do need the bounded degrees. So this is, so let's put this as a parenthetical remark. So that's circle packing and the connection to recurrence. So in order to show that the graph is recurrent, it's enough if we can demonstrate a circle packing of the graph. Well, if we have bounded degrees, it's enough if we can demonstrate a circle packing of the graph which is locally finite, has no accumulation points. And it doesn't need to be unique, so this holds even if it's not triangulations. So let's move to the side. So this is one component, and how much time do I have?
30 minutes.
Oh, good. You're just bored. Sorry, this talk is not aimed for you, really. Yeah, so, right, so how do Benjamin-Schramm use this result? Well, they say the following. So take, so let me review a crucial bit of the Benjamin-Schramm proof. So take a circle packing of Gn. So this is some configuration of circles associated to the vertices. And take a limit of those. So limit, and this gives us a circle packing of the limit graph G. So if you have so we need to normalize the circle packings, and we normalize them so that the root vertex is a circle of radius 1. And then the adjacent vertices have circles adjacent to that. We don't know that the circle packings converge, but we can take a subsequential limit. There is some compactness here where the bounded degrees is also useful. So up to taking a subsequence, we can find a circle packing for the limit graph G. And then we show that this circle packing is locally finite. And the way this is done, so it's a very clever lemma in the paper there. So recently we also have other proofs of this argument bypassing the need for this lemma, but the lemma roughly says that for any finite set S in the plane has at most one accumulation point relative to most points in the set. So this is not the precise formulation, since a finite set cannot have any accumulation point. So it's an approximate accumulation point. So what is an approximate accumulation point? It's if you have lots of points in one area. So what this says is that specifically, and what is relative to most points, of course, if you have a point, you can always squish everything so that everything is in one area. You need to scale things relative to the point. So what does this mean? We choose X in S uniformly. And we consider the event that there exists some point Q such that if you look at the, sorry, there's one more step before, which was there exists Q, and scale such that the nearest point is at distance 1. So if you have some collection of points, so if this is the point that we happen to choose, then we scale everything around this point so that the nearest point will be 1. And now what we consider is the event that there exists some point Q such that the ball around X of radius R minus the ball around Q of radius 1 over R. So this intersection with S is larger than n. So we want to have more than n points. So what does it mean? I take a ball of radius r. So this is the ball of radius r. Let's throw in some cluster of points here. And this is a small ball of radius 1 over r. So if I remove, this small ball, then I ask, so the question is it possible by removing such a small ball to have more than n points, to have less than, sorry. Is it possible by removing such a small ball to end up with a small number of points outside in the ball of radius r? And the lemma is that the probability of this tends to 1 as n tends to infinity and r tends to infinity. And this is regardless of how large the size the set S is. The crucial point is that you can take a set S to be arbitrarily large. So what this means is that if you take some set of points in the plane, you choose uniformly one of them and you scale around it, then it's very unlikely that if you have the center point here, it's very unlikely that you will have lots of points here and also lots of other points maybe near another point. Yes?
It's probability with respect to
with respect to choosing a uniform point in S. So this is a uniform in the set S. You can take any set S finite, and if you choose the point uniformly, then this is very likely that you can find such a cover. So it's not true for every point X. It's possible to have sets where some points X this will not be the case, but if you try to have such an example, so what would a bad example look like? So basically you want to have some point X and you want to have two large clusters of points so that you can't cover both of them with a small disk. But then when you choose a typical point with high probability, you will be in one of those if you have lots of points here. And if you choose this as your point, then now you suddenly rescale so that the nearest point is at radius 1, and now the ball of radius r only covers those points. So you don't see this second cluster.
The size of S must go to infinity as well when n goes to infinity.
No. Well, we apply it for sets which go to infinity, but this probability, so if the set S is less than n, the probability is 1 trivially. So, but this doesn't matter what it doesn't matter what the set S is, and I should mention one of the things that Gurel Gurevich and Nachmias did is to go through the proof and make this quantified, and basically, essentially, the proof that's in the Benjamin-Schramm paper can be quantified. So Itai and Gurel Gurevich and Nachmias did this, and they say that this probability is 1 minus constant. You get something like log of r divided by r squared, and where does n go? Sorry, it's yeah, sorry, I forgot the exact quantification, but maybe it's log n. Let's go with that. So there might be some slight mistake with this, but we do need a quantified version of this. So this is yes.
Is there anything planar about this fact? I mean,
it's true in higher dimensions.
Yeah.
It's true.
A different quantification.
Yes, it's true in any metric space with volume doubling, and the original proof more or less carries through. So the quantified form will have an exponent there depending on the dimension of the space, but yes, this is a more general statement. How does this help us, by the way? So so we take the set of points to be the centers of the circles in the circle packing. So if you take the centers of the circles in the circle packing, and now you rescale things so that the root vertex has a circle of radius 1. And what you get is that with high probability, you do not see 2 clusters of points within radius r. And this is true for any r. And consequently, when you take a limit, within any finite radius r, you do not see a large number of points. So the log n should be in the denominator sum. So this should be something like n squared. That's more like it. So, so with high probability, you do not see too many points within any radius r, which means, and this is uniform in the size of the finite graph, so when also true in the limit. So also in the limit, you see at most 1 accumulation point. So there is this one small point here where you could have some accumulation point hiding here in the limit. But okay, but this we can recover because we know that the graphs we have are locally finite, so they don't have any accumulation points. They are topologically a plane, so we don't get these accumulation points in the finite in the limit of the circle packings, and so it follows that the circle packing of the limit is locally finite. Is there any question?
So we're just asking about quantifiers for all S.
Yeah, for all sets S, for all R and N, the constant is universal. Okay, so that's all the ingredients basically from the proof of Benjamin-Schramm. I roughly hinted at how they are put together, but will not go over this in much greater depth since there's several more things that are needed. The next step is some ingredients from Gurel, Gurevich, and Nachmias. And we have the graphs with unbounded degrees. So one thing that they did is get this quantified version of the lemma. The second one is to turn a graph with unbounded degrees into a graph with bounded degrees. So here's the idea. You say that if you have some graph and you have some vertex of high degree, and this is called a star, then you replace the star by a tree which has bounded degrees. So you just replace this. So you have the same 6 edges going out, connecting to other parts of the graph, but instead of having a single vertex of degree 6, you put here some binary tree. And you keep it as symmetric as possible. So if you had 7 edges going out, then you will do something like that. And this connects to the rest of the graph. And you do this for every vertex with degree more than 3. So this takes a graph G and turns into a graph, let's call it G prime. You can do this for Gn, for the finite graphs. This turns it into finite graphs which have bounded degrees. Now, these finite graphs have bounded degrees, so if we take a local limit of those, they are finite degrees bounded, so the local limit of those is recurrent. Now, if you want to go back to the graph Gn, all you need to do is take all of these vertices here and contract them to a single vertex, and you need to do this everywhere. And this, in general, can turn a recurrent graph into transient, such contractions. So we need to estimate the effect of these contractions. And there's a small lemma, which again, I will not prove, but I will just state that if you take the resistance between 2 sets A and B in Gn, and you want to compare it to the resistance, so this is the electrical resistance, you want to compare it to the resistance between the same 2 sets in Gn prime. And I'm a bit fuzzy here about what it means to take the same two sets because it's not the same vertices, but you have some natural projection and you do this in the natural way. So the resistance in here in principle can be smaller than the resistance here, but it's at least this divided by the maximal degree. So if you have bounded degrees and here you have a resistance going to infinity, then here it also goes to infinity. But if you have bounded degrees, you can also, there's also some hope. So where did I put the eraser? Yes. So and the reason that there is still hope is, and this is roughly how Gurel, Gurevich, Nachmias finished their proof. So they say the following: let's take some limit of Gn prime. Let's take a large ball of radius r. Let's do a circle packing. So by taking a limit of the circle packings of the finite ones. So sorry, you take the circle packing of Gn prime and take a limit. So if you take a ball of radius r, then with high probability you have at most roughly r squared. And I think I remember now. Yes, okay, so I won't get into this, but with high probability you have roughly r squared vertices in the ball. And this is now a Euclidean ball in the plane. So that's what the lemma gives. And from this we deduce that the maximal degree inside the ball of radius r. So inside here you might have some, okay, and this is apart from some small clump like this, which might be bad. But from this we can deduce that the maximal degree in BR minus this B1 over R around the point Q is at most some constant log R. So that's a standard, that's using the exponential degrees, exponential tail on the degrees, and some small additional arguments. From this, we deduce that the resistance between the root rho and the complement of the ball is at least, so this is the resistance in G prime, in the limit of the Gn primes. The resistance from here to the outside is at least log R. This is using a comparison of the resistance on the graph to resistance in the plane, using the conformal structure, using the conformal type of the circle packing, the relation to conformal map. So if you have a graph with bounded degrees, this is the case. This essentially goes back to Hennenfent. So the resistance in G prime is at least log R. And together, we find that the resistance in G between the root rho and the complement of the ball of radius R is at least some constant. So the resistance is at least a constant, and now we let R go to infinity. And this doesn't give us recurrence. We want the resistance to go to infinity. But the observation, one more observation, is that you can replace the rho here by any finite set. So if you take some finite set K, then you also get this. If R is large enough. R needs to contain the set K and sufficiently far beyond it. So So what we have is that for every set K, there exists some R such that the resistance from the set K to BR complement is greater than C. And this is easy to see implies the recurrence of the graph. So this is true for any graph embedded in the plane in any way. So that's components from Gurel, Gurevich, and Nachmias. And now we come to finally to the new components that in my paper with Gurabrey. And the first thing is a decomposition of the half-plane UIPT into layers. So this goes back in some form to Krikun for his work on quadrangulation, and has also been used by Courien and Legal for the work on first passage percolation. And the idea in the half-plane UIPT is you get a particularly simple form. So you take the boundary of the half-plane UIPT, and you take everything adjacent to it. And this is going to be our first layer. So the first layer will contain lots of faces like that. And you have some faces which have 2 vertices on top and 1 vertex on the bottom. Let's make this a slightly bigger picture. So we see some things like that, and what happens is that you have some things in here. So as we've seen before, if you take some set in the planar maps, it might disconnect the complement. So we have some areas here where, so there could be several vertices on the boundary here. So we could have some areas here, and let's use some color, where you could have some arbitrarily large parts of the map. And these occur in these sets, in these parts of the map with a single vertex on top. So we have such a decomposition into blocks. And once you take this, what is known as the domain Markov property for the half-planar maps means that the rest of the map has the same structure, and it's independent of what we saw here. So in the rest of the map, we have, again, the same type of structure into blocks like this. And again, you can have some large parts of the map here, possibly small. So you have a sequence of blocks like this. And this gives us a layered map, a layered structure for the half-plane map. So you say you have the first layer, and then you have the second layer, you have the third layer. And these layers are all independent of each other. And you can even say more, because we know everything we want about the half-plane UIPT. So we know the size of these blocks. So these blocks are independent. So you have independent blocks. We know that these blocks have a power tail on their size. So the probability that the size of a block, so if this is K, the probability of K is some constant K to the minus 5/2, with the exception of the block containing the root. So if you have the root here, so the root is a typical vertex on the boundary. It's more likely to be in the bigger block, so the root has a size-biased block. So let's draw this in red for size-biased. And the same thing happens in the higher layer. So above, so if you take this to be a root for the higher map, then above it you get a size-biased block, and all the others are independent. And then again, above it you have a size-biased blocks, and all the others are IID. So we have this layered structure for the map. And once you have such a layered structure, there's a natural thing to do, which is to extend it. So let's delete this to make room, and we just add more layers below. So we add layers L0, L1, L2, -1, -2. And here we put the same structure. Well, it's the natural thing to put here is not to have a size-biased block. So here you just have, such vertices, and you have only the unbiased blocks. So like so. And you keep going down. So this gives us a full plane map. Let's call this M. And the half plane UAPT is obviously contained in the full plane map just by taking the higher half. So we have a random full plane map, and we know that H is contained in M. And what we prove, in fact, is that the map M is recurrent. Now, in order to prove that the map M is recurrent, the idea is to try to emulate the proofs of Benjamin-Schramm and Gurel-Gurevich-Nachmias. But there are some difficulties because the map M, we don't get it as a limit of maps with a uniform vertex. How much time? 5? 5. 15? 5. But there's a break, yes? Good. So we run into a big problem that we cannot get the map M as a limit of finite graphs with a finite, with a uniform root. But what we can do is the following. So let's take the half plane map, and let's take some large number of vertices along the boundary, and let's take the first k layers, which is also large. And I take this graph, this is my finite graph. So this is going to be my graph Gn. But what I take, I don't take the entire map to be, the entire graph and take a uniform root. What I do is I try to choose the root in a smaller set. So I choose the root rho n, uniform in the skeleton. So the skeleton is the map minus all of these bits here that I did not draw. So I take the root either on one, so basically I take the root just to be on one of those lines, on one of those levels. Now this is a small fraction of the set. If this graph is fairly large, it's much larger than n over k. So I have here n times k vertices, and there are far more vertices in the holes than outside the holes. Otherwise, I could just get by absolute continuity of the limit measures the recurrence. But I take the root uniformly in the skeleton. And now, what do I get when I push through the proofs of, when I go through the proof of Benjamin-Schramm in the quantified version? So I get that inside the ball of radius r, so inside here I have at most approximately r squared skeleton vertices. So I might have far more vertices on top of this. This is in the ball, and this is if I exclude some small clump where I might have a larger number of vertices. However, the crucial observation, the skeleton disconnects this map. So if I remove the skeleton vertices, then all I'm left with is those yellow clumps which are disconnected from each other. They are only connected through the skeleton. So that means that I have here lots of small, so where's the yellow? So I have here lots of small things, yellow triangles like that have large number of vertices in them, But they are surrounded, everything is surrounded by a polynomial number of skeleton vertices. And then by looking, by more standard arguments, looking at the structure of this map and looking at the degrees which have exponential tail, from this we deduce that the maximal degree is still at most logarithmic in R. So if you apply this to the original graph, the maximal degree is still logarithmic in R. So to be precise now, what we do is we apply the star-tree transform, we apply it to the graph after the star-tree transform. So all vertices that we get here are still come originally from vertices of degree at most log R, and the rest of the proof goes through as before. So the meta theorem that is really unstated here, the more general criterion that we get is something like the following. So if you take some graphs Gn, and you have some set Sn inside Gn, and I'll finish with this, and this disconnect Gn to, let's say, to components, and these components need to be small. We need to have some uniform control, some exponential control over the maximal degree in the components, both in the components and in the size and in the vertices in Sn. Then the limit of Gn with a root rho which is in Sn, a uniform root in Sn, this limit is recurrent. And that's what we do here. We have the skeleton, which is this set of vertices. They disconnect the graph completely. And when you take a uniform root here, then the uniform root is going to be quite far from the boundary. So in the limit, you just see something like that, so in the limit, you see this infinite map M. And consequently, it's recurrent, and consequently, the half-plane UAPT is recurrent. And consequently, I'm out of time. So I'll stop here and thank you all.
Okay, thanks for the beautiful talk. Are there questions? Bring you the microphone.
So does this imply that some matter-coupled planar maps are recurrent?
That's a very interesting question indeed. And the question, so for the matter-coupled planar maps, so there is a first step which in some cases can be done of showing that you have a local limit. And if you have the local limit with the exponential control of the degree, which again in many cases we can get, then it's recurrent. So this follows from Gurel, Gurevich, and Nachmias. If you take something coupled with matter in the half-plane topology where you have a boundary, then it's very conceivable that you could get things to work also in those cases. Again, you would need some estimates over size of components, maximal degrees in these components. There might be some other ways, some other decompositions that might be useful, but that's.
Other questions? Yes.
The resistance to infinity, how does one expect to grow it actually? So here there is no lower bound on the growth, right?
Indeed, so that's a very good question, and that's also in the UIPT something that we would very much like to know, how does resistance to infinity grow? And the second closely related question is how do the return probabilities to the origin grow? And this could be measured again in two ways. You can measure the resistance to the ball of radius r when you use the embedding using the circle packing or other conformal embeddings of the maps. Or you can use, consider the embedding in the graph radius. You consider the resistance to the complement of a ball of graph radius R. Now, we expect, in these cases, we expect the resistance to grow logarithmically. We expect the return probabilities to decay like 1 over n at time n. This is open, even if you have the UAPT with bounded degrees, well, okay, if you have bounded degrees, then it's easier, but for the UAPT, it's certainly open. So in some sense, the bad things that can happen in this case are if you have large degree vertices that tend to clump together and arrange in some patterns which allow you to significantly change the resistance. And this is something that doesn't appear to happen. And all the examples we have are built on forcing such things to occur. But yeah, that's a very interesting question.
Other very interesting questions? Seems to be one.
So you take the circle packing of the finite graphs and you see that locally they look like a circle packing of the infinite graph. And is there some similar thing? No, not similar thing. Results on the scaling limit of the circle packings. For example, if you take a triangulation of a large disk and circle pack it in, for example, an Euclidean disk, and is there some results on what happens when?
What happens? For this local structure, there is something called the ring lemma, which gives compactness of local structure. If you have a circle and you have 10 circles surrounding it in a ring, then the set of possible angles between them and radii is compact. So you don't get that you have convergence, but you have a subsequence that converges. And technically, all of these proofs show that if you have any sequence of these graphs, then any subsequential limit is recurrent. And so if you know the limit is recurrent, if you know any subsequential limit is recurrent and the limit exists, then you're good. So this ring lemma holds for other types of circle packings, for other types of embeddings, for many other types of embeddings. So you have some such forms of compactness for conformal mappings, for square tilings, for many other types of embeddings. There are some embeddings which do not have this, but in general, you do. So I'm not sure if you had a more specific setting, then maybe we can talk about this later. But.
Thank you.
Okay. If there is no more questions, let's thank Omer again.